All right. So have a nice day, everyone. This video will I will show you how to or I mean I will begin to discuss here all about the shortest path algorithm. Now, let's try to find out first what is a shortest path. So when we say shortest path, that is an algorithm that is designed essentially to find a path of a minimum length between two specified vertices of a connected weighted graph. So in our graph, we will be going to find the shortest way, or this is a minimization type of algorithm. So we also defined as the minimum cost route from one vertex to another. So the application for this will be a map. So the shortest path is a common concept in our graph theory, actually, and especially in computer science, since it refers to the path between the 2 points or a nodes in our graph that has the smallest possible sum of the weights, or it could be the distance on the edges between them. So the popular real-world application of finding the shortest path in a graph is stated right there is a map, which navigation is made easier and simpler with various shortest path algorithms where our destinations considered with the considered vertices of the graph and routes are the specific edges. So the two common shortest path algorithms stated right there will be the Dijkstra'S algorithm as well as the Bellman-Ford algorithm. So in this video, I will begin to illustrate first how to come up or how to do the uh we will begin to dive into the Dijkstra's algorithm before we'll tackle the Bellman-Ford algorithm. So Dijkstra's algorithm that is designed to find a shortest path. So since they are working between, I mean, shortest path between two vertices of a graph or from a single source node to all other nodes in a graph with a non-negative edge weights. So it does not allow here to have any specific negative in our Dijkstra's algorithm. It's commonly used for applications such as this GPS navigation, network routing, and other pathfinding problems. So next, it was designed by or published by Dr. Esger Dijkstra, a Dutch computer scientist, software engineer, programmer, essayist, and a system scientist. So each vertex in this algorithm will have two properties, which is the visited property as well as the path property. So the algorithm that we follow, we will begin at the node we select or the source node, and it examines the graph to find the shortest path between that node and all the other nodes in the graph. So I know that it's Vegas for now, but we will picture it out later on. Now, the algorithm keep records of the shortest distance, or I mean, records of the presently acknowledged shortest distance from each node to the source node, and it updates these values if it finds any shortest or shorter path. I mean, next, once the algorithm has retrieved the shortest path between the source and another node, that node is marked as visited and included in the path already. So the procedure continues until all nodes in the graph have been included in the path. In this manner, we have a path connecting the source to all other nodes. We following the shortest path to reach each node. So here then, a graph and source vertex are requirements for Dijkstra'S algorithm, and that algorithm is established on grid approach, and thus finds the locally optimal choice or the local minima in that case. So at each step of the algorithm. Let's move on here. We also do have, as what being mentioned earlier, we have the visited property as well as the path property. When we say visited property, that is signifies that the node has been visited. Uh, we do not revisit the node. We are not allowed to revisit. And it is being marked as visited when the shortest path has been found. And the property stores the value of the current minimum path to the node, implies the shortest way, and will store the final answer for each node. Initially, we mark all vertices unvisited and set to infinity apart from the source node, which is 0. And we are doing the relaxation, which if your D and the cost of your U and V, if it is less than the distance of the V, so therefore we will begin to update that the distance of B is equals to the distance of U plus or sum to the cost of U and V. You will add everything then. Let's actually picture it out later on. How does it work? Now, let's try to figure out here then how does the Dijkstra'S algorithm work. So we will be going to work on the Dijkstra'S algorithm in an undirected graph. So let's move on. So in our undirected graph, suppose that we do have here, say for example, so our 0 is that was here. Let's try to see. This is the 0, and everything, since we wasn't able to visit yet here, we set that as infinity. So that is infinity as right now. Afterwards, after we will apply the cases. You will start from the source node and only move to adjacent neighboring nodes. So what will be the adjacent neighbor for A? That is C and B, right? And you will find what will be the shortest path right there. So it will work by exploring the closest nodes first, expanding outward layer by layer, much like a wavefront. So that's how it works. So what will be the minimum cost right there? So that is 8. So we can go to 8. So we will visit A to B. That is 8. So we will, since 8 is smaller or shorter than infinity, we cancel infinite and we change that into 8. So we update our table here as 8. And our A is 0 as a minimum shortest path already then. Now, afterwards, you will find where will be. There will be B to F and there will be A to C. So what will be the edge that do have a shortest path? So that is 12. We can visit A to C. That is 12. So right now, we update 12 and cancel the infinite. And afterwards, after you visit, this will be the step 3 already. We do the relaxation. So the distance of U and the distance of B. So we will calculate 0 plus 12. And if your cost of your distance V right now, if it is greater than and greater than the value or the cost of your U and V, therefore we will update or cancel this one and update your distance of V into the new cost of U and V. That's how it works in the relaxation steps. Now, next step, there will be from C to E and B to F. That will 34 plus 8 12 plus 19. So we can go through C to E first. That will be 31. By adding 12 plus 9, that is equals to 19. And since 31 is less than infinity, so we update the letter E. So that is 31 right now. Now, we already examined and the visited is already A, B, C, E. We cannot revisit that. And here now, we will do the E to D, 31 plus 14, or B to F, 34 plus 8. So we can go for the step 5. We can add right now, sorry, the step 5, we will be going to add the 8 plus 36, di ba? Ah, no, 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 no. That's not, we can have here A, B, C, E. So afterwards, you will visit the letter F. So by visiting, wala pa ni tani supposedly here. I'm so sorry. I'm so excited to update that one. So 31 plus 5, that will be 36. So we update here because 34 plus 8 is much greater than the value. So that's why much better here. So 36 is updated and cancel the infinity. So we visit already A, B, C, E, F. Supposedly ha, wala pa niha. So just don't mind that in the step 5. And in step 6, we'll visit the letter D by doing the A, B, C, E, F, then D. So the visited right now is A, B, C, E, D, E, F, D by connecting E to D, which will be 31 plus 14. That will be 45 because it will be more if 36 plus 30. So that will be the lowest value or the shortest path right now in your using Dijkstra's algorithm for undirected path. So A, B, C, E, F, and letter D. That's how it worked for the visited. It won't matter here then. It's okay if you wasn't able to update that one. As long as you updated your table here in each step. So you will calculate the total shortest path distance from 0 plus 8 plus 12 plus 45 plus 31 plus 36 and your shortest path algorithm for the Dijkstra's algorithm in that undirected path will be 132. So that's how it really works. So in the next video, I will present to you how to work on into the directed path because it will be um hard by doing the undirected path since the path is connecting both and vice versa. So I will also um provide a video for directed graph.